Good morning, everyone. Thank you for the introduction. Thank you for thank you for getting us here this morning. Thank you guys for all being here. We're excited to talk about the possibilities of a partnership between National Instruments and Opal Rt. Let me skip ahead to my slides. There we go. A little bit of background before I get started about National Instruments. We all know who Opal Rt is. We're all here because of the history and because of the work that Opal Rt's done, but you may not know a whole lot about National Instruments. Our goal as a company, starting in 1976, was to equip engineers with the tools to accelerate what they do. Our mission is to give scientists and engineers the best possible tools to do their job most efficiently and most effectively. One of the keys to that as a large company is that we've had stable growth. It's not quite the growth curve that Jean showed yesterday, but over the last years since 1976, we've shown significant growth, and I think one of the key pieces to that is the reach of our company. We're 7,100 people in about 50 countries, and we're spread out across a large number of different areas in the industry. No one specific slice of our revenue comes from no one specific piece of our revenue is more than 15%. That means no industry dominates the work that we do. We're spread across a huge area of the market. Another key to our growth is our continued investment in R&D. NI believes that the way that we continue to innovate as a company, the way we continue to bring these tools to our customers is by investing heavily back in our R&D. So about 16% of our revenue goes back into our R&D facility. And that R&D facility is creating what we think is one of the best platforms for design, test, measurement, control systems in the world. And the key to that is being able to use off-the-shelf hardware to speed innovation. It gives us the ability to produce high-level software and flexible hardware that has an open platform for us to grow and build upon. At NI, we call this platform-based approach our idea of graphical system design, where we map the various industries in which we work, measurement, test, monitoring, embedded control, to the platforms, the hardware components that we build and that we design. And the key to bringing this together is the IP of our engineers, the IP of our customers, the IP of our partners that sits on top of the application space and sits on top of the hardware and is tied together with LabVIEW, our programming environment. Many of you might be familiar with LabVIEW. I had a conversation with people last night talking about they use LabVIEW. They remember LabVIEW from that one time in college, or that was 2 times in college. A lot of us have had some exposure to LabVIEW. LabVIEW is a graphical design software package. RT is written in LabVIEW. Some of the LabVIEW look and feel, if you're an RT Lab user, will feel pretty familiar. The piece that we're excited to talk about today is that application of LabVIEW and the application of the platform to our embedded target platform. The Compact Rio, the MyRio, the devices that you see up here and that you can see closer probably later have a processor for real-time control tied directly to an FPGA with a modular I/O system. That processor is running a real-time OS and various networking protocols. The FPGA, we can put our graphical programming environment into that FPGA directly, no VHDL required, graphical programming of the FPGA. And then we have an open platform for our I/O modules, whether those are analog, digital, specialized communication buses. We have an I/O interface that's open and flexible, tied together with LabVIEW. So here is the Compact Rio. This is a slightly different version of the Compact Rio than we have up here. But in the picture, you can see a processor. You can see the FPGA and the blue modules on the screen and the gray modules on the screen. Those are the modular I/O components. It's a rugged platform. It's high performance, depending on kind of the family, depending on the device used. That has an embedded processor up to a dual-core i7 processor. And it has a full suite of analog, digital, communication bus I/O that's not just supported by National Instruments, but also supported by a large list of our partners, and accessible in the graphical programming environment. one of the pieces that, that really makes these devices that we're talking about today unique and different from some of the previous iterations of these devices is that these pieces here are built upon the Zinc architecture, which is a new architecture from Xilinx that takes the FPGA and a real-time processor, FPGA, and an ARM processor and puts them on one chip. And so very close tie then between the processor and the FPGA directly tied to the I/O. The other really exciting piece that Jean mentioned is the MyRio hardware that we have created specifically for the academic space. It's an academic embedded target designed for lab and student use. It's a very low-cost target that is designed to enable students to learn embedded control and embedded design effectively. And we've taken this MyRio target and we've taken the compact Rio, and we realized that that gave us an opportunity to figure out how National Instruments and Opal Rt can better work together to map some of that amazing Opal Rt IP, the years of experience that Jean and that Opal Rt have built around the space of power electronics HIL, map that into LabVIEW, run it on Rio hardware, and enable students to really explore the concepts of control and HIL for power electronics. So to do that, we've taken a graphical approach to wrapping up Opal Rt IP and solver and run that on this Zinc-based compact Rio. And the end goal of this is to put together a platform for teaching the design V, the design process for power electronics. The MyRio on the left-hand side of the picture could be connected to a real plant, a physical motor spinning, a physical circuit, or it could be connected to the HIL system to be able to simulate that physical plant. And the students can then do algorithm development on the MyRio and then test that algorithm against things running on the compact Rio. It gives students the ability from undergraduate to graduate to research level quality of test and design, really empowering students, we think, to really understand and know power electronics, HIL, and control. We think that this will be a very exciting element for us to explore the partnership between National Instruments and Opal Rt. With that, I will go back to Jean.
The main idea behind this project is to make the FPGA programming easy. So those who have worked with this type of technology understand that this is complex, this is long, it takes a long time to compile, it takes several weeks to design. So if you want to even implement such a small circuit, it takes time. So our idea was to pre-compile a solver inside the FPGA itself in order to reach time step below 1 microsecond. Like what you see here, the time step could be quite low. Then the user, the main point that the user start from is from a graphical interface. It can be SIM power system, can be Plex, can be PSIM, can be any type of software. And we hope to use the multi-SIM from an I also. So the engineer starts from his own simulation tool, make his network, make the simulation, and when he is happy, then he can automatically generate the code. So these are examples of circuit that can be simulated, and I think that this afternoon we will have a more detailed presentation about that. So the idea is to reach very small time step, because now in the aircraft, automobile, and microelectronics for PVs and microgrid, the converters work very, very fast. So if you want to invent new technology, either you have to build your own analog system, your own bench, and make your development with the bench, or you start to use this type of technology. So these are examples, basic circuit like the boost, the AD-H bridge, but then we can go with more complex three-level inverter, which is it's this. Now, if you start to build your own analog bench for that, it starts to be more expensive. It's more complex. If you want to study fault, short circuit everywhere, then you don't want to break your bench or you don't want to make the tests. So, but if you are in simulation, you are allowed to do whatever you want. So you can see in the circuit at the bottom now we can have motors, we can have rectifier or grid connected circuit. Okay. Then you can try to have the new type of topology like matrix converter. So these are quite complex. So you can study it in offline mode. In offline mode now at this type of time step, it will take a long time. But then if you want to go faster and if you want to interface a real controller, then you can download the code to a small FPGA. And if the problem becomes larger, you use a larger FPGA or you use many FPGA interface together. Okay. So then you see this is like a PV system where we have many EHS solver. So we can grow the complexity of the system as we want. Okay, so this saves time, and because the solver is always running, this means that you can change parameter, you can change the topology while the system is running. So you don't need to regenerate code. So you can view that as a platform where you will remove a resistance, put a diode, change the polarity. So this is quite fast. So now I will give the microphone to Pierre-Yves, he will do a live demo. And be careful, we always have the demo effect. So wish you good luck.
Okay, first I'll introduce you to EHS. EHS stands for Electrical Hardware Solver. So it solves electrical circuits, and we say hardware because, as Jean said, we use the FPGA device on the Compact Rio to accelerate the simulation and have a much higher sampling frequency. I decided to present you the demos first because I'm confident that the ease of use of that tool is so good that you'll understand the demos even if I didn't explain the technical details behind the EHS before the demos. So I have 3 very simple demos. At least they will appear very simple to most of you because they are intended to be used in an educational laboratory for undergraduate students, for example. The first demo is a diode bridge rectifier. What the teaching objectives that I included here are, for example, what the student should learn with this. So as it's the first example, I would say it could be used for the students to learn the tools, learn LabVIEW, the use of LabVIEW, etc. And then to understand the pretty simple operating principles of the diode bridge rectifier and to observe the effect of the load type and the load impedance on the observed signals. So we'll switch to the demo. So this is my LabVIEW project that was already open. I also have my rectifier VI that I'll bring to you right here. And I'll deploy the model. So now the simulation is running. It was as simple as this, and I'll show you a bit how this VI is the LabVIEW model, which is composed of this front panel and also a block diagram behind. But for the student, normally they will only need that front panel. On the top left corner here, there is a choice of scenario. So normally in a lab argument, there will be a list of things to do, and the first thing would be, for example, to select a scenario. So you could select, for example, the scenario with a resistive load, and we would observe the effect of varying the source amplitude. here we have the electric circuit that we are simulating. The type of loads that are connected with that scenario. So it's basically resistive load. What's written? Resistive load with 470 microfarad capacitor. So you could observe here that with a source amplitude of 100 volts, peak to peak, no, ground to peak, we observe an output voltage that is rectified at around 175, but with you see the ripple of the output signal of around 25 volts, something like this. And the next step might be to choose a different scenario, for example, to add an additional output capacitor. So the output capacitance was increased by 1100 microfarad or something like this. So we could observe that the rectified voltage went up, and you can also see the effect of the RC load here. So the capacitor charges when one of the diode conducts, and then when the voltage goes down, at one point the capacitor holds the voltage. So that's why the voltage stays a little more flat after this. We can also change the source frequency, for example, to 60 hertz, and we can observe the difference in the ripple here, for example, or also a higher frequency, let's say 120 hertz. So the ripple is again smaller. So that's more or less how this demo would work. You could also ask the student to observe the power. Now it's, I think, the Y. So I'll go back to the default scenario. So you could ask the student, for example, to prove that the output power, so the power that you can provide to the load, which is simply the voltage times the current, is the sum of the three powers that the sources, the three-phase sources, provide. So for this, for example, you could say export to Excel, for example, export to Excel, and then in Excel make any mathematical operations you want to prove that the sum of the three green, blue, and red lines are equal to the yellow line. If we go back to my demo, my PowerPoint, I'll show you the next demo. Next demo is a boost converter. So the goal would be to again understand the operating principles of a boost converter. If any of you don't know, when the switch here is closed, there will be current accumulating in the inductance. And when the switch is open, that current will come here and charge the capacitor. And also, again, we will want the student to learn how this works. So basically learn how a diode works, an inductor, a capacitor, etc. And explain the effect that is observed on the output when we change the load, for example. And there are two modes in the boost converter. It can be either in continuous mode or in discontinuous mode. So when you're in continuous mode, the input current never falls to zero. While when you're in discontinuous mode, it will fall to zero. So we'll go back to my project. Maybe I'll close this one. close the rectifier, open the boost. And I'll deploy the model. So again, the VI is very similar, except that here what we will be able to change is the source voltage. And as we have a switch, we can control the switch, and we can specify the switching frequency of the PWM signal that will be sent to the switch and the duty cycle. So again, there are scenarios. Let's say the basic one would be to observe the voltage output by varying the duty cycle of the PWM. So now the switching frequency is very low. So that's why we have a very big ripple. But let's say the principle would be that the output voltage will be higher than the input voltage, and that's the object of the boost converter, which is a DC-DC converter. So we can see the effect if we decrease, for example, the duty cycle. Now it's 85%. If we go down a little, we will see the output voltage going down too. And in the bottom scope here, the green line is the input current. So we see it going down here, and when it goes up, actually it's just under the red line. So it goes up. When the switch is closed, the current accumulates in the inductance in the inductor, and then when the switch is open, the current flows into the output capacitor and RC in the output. So as I said, one of the goals could be to try to find that limit between the continuous mode and the discontinuous mode. So the lab argument would say, try to find the duty cycle interface in between. So we see that now at 79%, we are still in continuous mode. So I'll just bring it down a little until I see the green line staying at 0 for some time when the switch is open. Oh, I think we reached it, and it's at, I think, 69%, something like this. And if we go lower, we'll see the basically the switch voltage that will be different. If we change the circuit parameters, for example, I think I wanted to change the switching frequency to a higher one, for example, 180. We will see that limit between continuous mode and discontinuous mode changed. And basically, when it's in continuous mode, the output voltage only depends on the boost circuit gain only depends on the duty cycle of the switch control, whereas when you're in discontinuous mode, the gain depends on many other parameters, for the output current, the switching frequency, input voltage, something like this. So, and we can see here that it's still in continuous mode, so I still have to bring it lower a little, and we'll find the interface at around 49%, I think. I think it's here. So that would be the second demo. I'm not done with it, so I will just go back to my PowerPoint to show you the third demo. The third demo reuses the boost model. But now, instead of having my duty cycle controlled from my control in the front panel of LabVIEW, I made a little VI, a little PI controller on the MyRio. So we have the compact Rio, which is the one with the IOs that you can plug in, and there is the MyRio, which is much smaller, In this case, it's connected through USB to my laptop here, and I have one analog input inside that Mario that gets the output voltage of the boost, and there is one digital output that sends the control to the switch in the boost module. So I'll connect to Mario. And that's what Jean said, that there's demo effect. It says that it's unable to resolve, so I'll just try to unplug and replug it. So now it's running, but the loop is not closed, so that's why the duty cycle saturated near 1. I think I want to show you a little, because I said that it was, the VI is a front panel, but it's also a block diagram, and this one is rather simple. So if you don't know LabVIEW, I'll just show it to you here. So as I said, it's a simple PI, so I have a KP, KI, and I can measure the error between the load set, the V load, the output, the load voltage set point that I set in my front panel, and what I read here. Of course, the analog input is between, I think, -10 and +10 volts. So there is a scaling that is applied. So it's applied on the compact Rio to bring the voltage, for example, from 500 volts, from a 0 to 1,000 volt range into a -10 +10 range. And then we reapply the opposite of that scaling here to bring back the value at the correct scale. And this is the rest of the PI controller. If we go back to my front panel, I'll reopen the boost. So now it's still with the scenario I've chosen before, but if I go down here, we added a selector to select the external controller instead of the open loop. So I click here, and now the output voltage, the switching frequency is much higher, so that's why we don't have that ripple. And if I bring back my controller, we can see that I was asking for a load voltage of 250 volts, so that's what we observe here, and that gives a duty cycle of around 60%, it seems. And I can actually show you on the scope, maybe. So we can see the 3 kilohertz control PWM that is around 60% of duty cycle. If I increase the load set point, for example, at I don't know, 500 volts, we'll see the duty cycle go up. 800 goes up again, and now it's near 90%. And that's with a switching frequency of 3000. But if we bring it down, so I'll go back to something that looks like the open loop demo. So at 100 hertz, we should see the ripple that we had before, and we can make that frequency even much higher, let's say 5,000 hertz, and now the ripple is very small. So that concludes, I think, that PI demo. And one good idea would be maybe to ask a student to build the complete controller, for example, as it's a pretty simple model, so an undergraduate student will have a lot of fun, I think, implementing it on the Mario target. So that concludes the demos. I'll halt everything. Stop. And I'll go back to the presentation to show you some details on the technical sides of EHS. So first, what is EHS? EHS, it's a solver that runs on the FPGA that solves the circuit with the nodal approach, so the nodal current law. It solves the conductance matrix of the network and finds the voltage at each nodes and hence the currents. And the conductance matrix, it depends, of course, on the circuit. So it changes from circuit to circuit. But we don't have to recompile the FPGA bit file to do that. The solver is a generic solver. So the first step, if you want to change a circuit, is to design a new circuit. So this is, for example, our diode bridge rectifier. Second step, it's automatic. It looks like a step, but you don't see it. There's an automatic analysis of that circuit. Basically, the circuit editor gives us the netlist of the circuit, and we calculate the conductance matrix from that netlist. And then we simulate it. So basically, what you don't see the middle part. You modify your circuit, and then it can be simulated. The matrix is loaded automatically to the target computer, so either the Compact Rio here or any other compatible hardware, and the simulation runs in real time and at very high speed. So how does it integrate into LabVIEW? So this is just a concept. It was created by Ben here as the concept of having EHS, the EHS solver, as an Express VI, or I don't know how it's called, into LabVIEW. So it would be just really a drag and drop idea. The idea would be just to drag and drop the EHS block into your VI, and then you could start using it. I think this one is the CPU block, so basically the normal usage you would do. There would also be one if you need to do your own bit file for any reason. So if you have different IOs than the one that are in the default version. So there is a block for FPGA if you really need it, but basically people will mainly use the CPU block. If you want to modify the simulated circuit from a student point of view, when you're just doing your lab, you modify the circuit by choosing a different scenario. And all the scenarios are included into the block diagram of that VI. So you select your scenario, and if you remember well, you had drop-down lists for the output capacitor value, for example, the output resistor value. However, for if you want to modify the circuit deeper, so not only changing the values of capacitors, if you want to create a new example model, for example, then you have to update your circuit into a circuit editor. So that example here is with the SimPower System toolbox in MATLAB, but eventually we'll have other tools, maybe multisim from NI. So this example is the same diode bridge rectifier, but with an input. The input source has an RL component. So in that case, the behavior of the circuit will be a bit different. Sometimes two of the branches will be conducting at the same time. So that would be maybe interesting to show students and to make students understand that kind of circuits too. So if you want to create a new exercise, that's in LabVIEW. So basically, the access to the EHS block is again very simple. You have the inputs, use switch controls, and you get your outputs. Y here. There is here the PWM generation. So in the case of the boost, we needed PWM. Analog output. In the last demo, we needed our voltage as an output. So there is the part of the VI that manages the outputs here. So if you know LabVIEW, this will be rather easy. Now, what's the main reason of using EHS is to have a very small computation time. For example, if you have the boost or the two-level inverter here, as your switching frequencies will go higher, you will want to have a higher sampling frequency too. So these are examples of like 4 of the examples we have prepared. The two that you've seen today, the boost and the diode bridge rectifier, are here. There are sampling frequencies in the order of 3 megahertz for the boost and 2.16 megahertz for the diode bridge rectifier. So that frequency depends on the circuit complexity, and in our case here also in the number of scenarios that are included in the circuit. And we have 2 other examples here. The buck converter that runs the fastest in these examples. So it's 140 nanoseconds of sampling time. So that's 7 megahertz of sampling frequency. And the 3-phase inverter here runs at 420 nanoseconds. So that's 2.3, 2.4 megahertz. Now when we have the controller, the outside controller, the sampling frequency stays the same here. But of course, in the loop time, you have to include all the IOs. So for example, in the case of our demo here, the latency of our analog output is 8 microseconds. The latency of the digital input is 100 nanoseconds. And then to that, you have, if you want to compute the complete loop time, you have to include the processing time of the controller here. If we want to optimize it, we can think of, now the PI was implemented in the CPU part of the zinc, so it's slower. It runs in the order of hundreds of microseconds. But if you want to run faster, then you can use the FPGA side, and then the delay here will look a lot like this one. So because you have the analog output, the digital output here, latency, analog input, latency plus the controller itself. So we can think of, if this is roughly 8.5 microseconds, we can think of maybe 16, 17 microseconds for the whole system. Now, how can you design a circuit? We started the development with the SimPower System toolbox in Simulink, but in the last year we added the support also for Plex from PlexSim and PSIM from PowerSim. And in the future we plan the development also for Multisim from National Instrument and EMTP RV from EMTP RV. Okay, so as a conclusion, we saw that EHS was able to run and to simulate an electric circuit in the order of with a sampling frequency in the order of megahertz, so in the sub-microsecond sample times. We now see that we can have a low-cost solution, including EHS running on the compact Rio, and that makes that solution, that makes that product very suitable for a model-based test bench in another undergraduate educational lab. And we also saw that the flexibility of that solution not only enables you to simulate an electric circuit on the compact Rio, but you can also connect analog inputs and outputs to that simulation to have really a complete hardware in the loop solution into a laboratory into an educational lab. We presented you two very simple demos, and with the sampling time also of two more, but we can have even more circuits depending on what you need, and Opal RT has a lot of expertise with our EMS team. It's Jean's baby, and he's really happy to develop new models for to accommodate your needs. So thank you for listening. Do you have any question? Do we have time for questions?
Yes, we have. You hear me? 1, 2. Yes, we have 10 minutes for questions. So that's excellent.